Before I start out my presentation, here's a quick question. What common features do you see in the pictures I'm about to show? I'll give you a few seconds here. Perhaps you can identify it, but you're just unsure on how to express it. If you have this picture in mind or something similar, then you are right. In fact, this is actually a popular diagram and its correct name is the Fibonacci spiral. Before moving on with the Fibonacci spiral, I need to explain the basics first and how this spiral came to be. Maybe you have heard of it, but this spiral comes from the Fibonacci sequence. No surprise there. This sequence is formed when the next number in the sequence is the sum of the previous two numbers. For example, as you can see here, 2 is formed from 1 plus 1, 3 from 1 plus 2, 5 from 3 plus 2, and so on. In fact, there is another crucial piece of information that can be inferred from this sequence, and this piece of information is what makes it somewhat special. By taking the ratio of two consecutive numbers, this ratio will have a value closer to 1.618. And this ratio is called the golden ratio. On the left side of this slide, you can see that I have written down some of the values of the ratios in this sequence. In the first few ratios, they do not resemble 1.618 whatsoever. But from 34 divided by 21 onwards, the ratio becomes closer to the golden ratio. In fact, the more it goes on, the value almost resembles exactly 1.618. However, note that these ratios that I've written down are rounded off to 4 significant figures. So if you do the actual calculation of the ratios, you'll get a recurring decimal, and it may differ from 1.618. However, they are very close. Now remember the Fibonacci spiral I mentioned earlier? The Fibonacci sequence actually forms this spiral. Here's how. It starts at the small white square with a purple square next to it. These both are 1 by 1 squares. We add the length of these squares to form a new square to be drawn next to it. By repeating this process, we have the figure you currently see with a spiral line touching the corners of the squares. The length of these squares match the Fibonacci sequence 1, 1, 2, 3, 5, and so on. That is how the Fibonacci spiral is formed. Now, back to the question I asked earlier where I asked you to find some similarities between some pictures. Another common feature is that they all exist in nature. As you can see in these pictures, we can observe that a Fibonacci spiral is formed among them. These phenomena form almost a perfect resemblance to the Fibonacci spiral. Here's another quick challenge. Try thinking of something that also has the Fibonacci spiral. If you couldn't think of one, I don't blame you, because I couldn't do it either. Here's one example that I'm sure almost everyone has seen. Yes, an egg. And as you can see, it fits within the frame of the spiral. It's fascinating and oddly satisfying to me how it fits exactly within it. One less simple yet cool feature the Fibonacci sequence has is the conversion from miles to kilometers, and vice versa. For example, if I were to convert 34 miles to kilometers, all I have to do is to find the number that comes after 34 in the sequence. In this case, it is 55. Which will give me the distance in kilometers. However, this is only a quick estimation and not very accurate because the actual distance in kilometers is 54.7 kilometers, rounded off to 3 significant figures. Although 55 is not too far off from it, it is still not the most accurate, so I would refrain from using this as an actual conversion. Now, another flaw that this has is that you are unable to do the conversion from miles to kilometers for the first couple numbers, and I'll tell you why. So the reason why this thing works in the first place is because 1 mile is around 1.60934 kilometers. And if you think about it, it's actually quite close to the value that the golden ratio has, which is 1.618. And remember earlier in the ratios that I written down, the first couple ratios are far from 1.618. Hence why you cannot do a direct conversion for the first two numbers. But as the sequence goes on, and the further ends of the sequences, this will work more effectively because the ratios become closer to 1.618. Here are some other more complex uses it has. It is used in trading, seen in evolution, and used in agile estimation. Now, I know these terms seem a bit confusing, so I won't go into detail about them because they are rather complex and will require a more in-depth understanding of them. That about wraps up my presentation. Thank you for listening.